We have four exciting presentations ahead of us. The first would be by Shreyas Vissapragada. Did I read it correctly?
Yeah.
Okay. He's from the CFA and will tell us about why there are planets in the Neptune desert. And then after that, we hear from Vega from NASA Goddard. Is Laura here? Yes. She will tell us about exploring flares in simultaneous multi-wavelength observations of active and dwarf stars. And then we hear from Aldana Grichener. She is visiting us from the Technion, Aldana, over there. She will talk about mergers of neutron stars and black holes with the cores of giant stars. And finally, last but not least, we'll hear from Vishal Baibhav from Northwestern. Is Vishal here? Yes, great. And he will tell us about which came first, black hole spin or supernova kids. So we'll start with Shreyas. Go ahead.
Great. All right, can everyone hear me?
Yeah.
Awesome. Thanks for having me. Today I'm going to be talking about a part of the exoplanet population that I think has become quite interesting over the last few years, called the Neptune desert. So we've discovered a lot of exoplanets so far, of order 5,000 or so, and to make sense of the population, we often like to put them on plots like this. This is a planetary mass period diagram, and the different symbols indicate different detection techniques with which these planets were discovered. Circles indicate planets that transit their host stars, and squares indicate planets that don't. But both of these types of planets have had their masses measured by radial velocities. You'll notice a few familiar faces within this population, including the hot Jupiters. These are planets around the mass and size of Jupiter, but are on incredibly short period orbits, less than like 10 days or so. You also see this emerging lower mass population of these very hot planets, things that are up to around 10 times the mass of the Earth, which I've called hot Earths. Sometimes when they're short enough in orbital period, they're called ultra-short period planets. But in between those two populations, there doesn't seem to be anything. Indeed, as of 2018, the picture was exactly this. There were no known Neptune mass planets on very short period orbits. And we can immediately convince ourselves this is not a detection bias effect, because transits and radial velocities are better at finding bigger things that are closer to their stars, and we see smaller things and things that are further from their stars. So this paucity of planets has been called the Neptune desert, or the subjovian desert. And a compelling explanation for why we lack planets in this mass period regime is that they're just really hot. And hot planets can lose mass due to an effect called photoevaporation, which I'll explain schematically here. So these planets are getting bombarded by high energy radiation, X-rays and ultraviolet, here collectively referred to as XUV. That radiation impinges on the planetary atmosphere and can photoionize species like hydrogen and helium, generating enormous amounts of heat. And when that heating is strong enough, it can drive the planetary envelope to expand and ultimately for some of it to escape. In this sort of simplistic schematic sense, the amount of mass that the planet loses is proportional to the amount of X-ray and ultraviolet radiation that it receives. But that was the picture in 2018. Things have changed in the last 5 years, and for what it's worth, 2018 is not that long ago. That's after the majority of the Kepler planets were discovered, right? But TESS has already begun to find 5 or 6, I think there's one that's been discovered after this paper, planets residing deep within the Neptune desert, where we had absolutely no planets there even 5 years ago. So as of this year, the desert is decidedly not empty. Maybe we should stop calling things deserts. And that sort of raises the question as to why there are planets in the Neptune desert, which is the title of my talk. Some of these planets sort of make sense. In particular, like the higher mass planets, TOI 332 and 849, are effectively consistent in bulk density with being rocks that are orbiting their stars. And maybe that makes sense. You know, these planets couldn't hold on to their atmospheres, and indeed, they don't look like they have atmospheres. But far stranger are planets like LTT 9779 over there on the lower left part of this new population. And this planet is weird because it's low density. So here I'm showing LTT 9779 up there on the upper right of this mass radius diagram of exoplanets. Also shown are a few composition curves calculated by Li Zheng, showing what a planet's mass and radius would look like given a certain fraction of iron or water. Some of the ultra-short period planets from that first plot are also shown, showing that they're also basically consistent with rocks. But LTT 9779 has the density of Uranus and Neptune. This is a planet that even if it were unphysically 100% composed of water, that yellow line, would have to have some volume of hydrogen and helium to match its current size. Given our understanding of photoevaporation, we think that a planet that has hydrogen and helium at this close of an orbital separation to its host star should be losing it. Should be losing it fast and should be losing it now. For reference, the orbital period of this planet is 20 hours. So by the time you wake up tomorrow morning, it will have completed another orbit around its star. So it is getting baked, but somehow it has hydrogen and helium left. And generally, we're sort of agreeing on how much mass it should be losing from the modeling side, something like 10 to the 11 grams per second, which is of order an Earth mass per gigayear. So we think this is an ideal system to look at photoevaporation in action. And I'm an observer, so I really enjoy the fact that we can actually see this happening because we're lucky enough to see the planet transiting its host star. And when the TESS mission observed it, this is sort of what it saw, a light curve of brightness versus time, and you see these dips corresponding to the presence of LTT 9779b. And even if the planet's atmosphere is escaping, missions like TESS aren't able to see it because escaping material is quite tenuous and it doesn't block out very much light. It's very low density. But if we could observe at a wavelength where all of that outflowing gas became opaque, then suddenly the planet would block out much more light relative to other wavelengths. And by looking at that change in transit depth as a function of wavelength, we could infer the presence of a planetary outflow. This is a very nice, fun schematic, but, oh, and I should also mention the perfect wavelength to do this was discovered here at the CFA by Antonia Klopčić, who found that the metastable helium triplet at 1083 nanometers is the wavelength that sort of makes this happen, where all of this gas becomes strongly absorbing. But in real life, these detections are a bit messier than that plot that I showed before. Spectroscopic helium detections sort of look like this, where we use high-resolution spectrographs on Earth to measure the spectrum of a star that hosts a planet as a function of time. So what we're looking at is the star HAT P11, which hosts another Neptune-sized planet. The spectrum of the star is normalized to the out-of-transit spectrum. So what you're looking at is the excess absorption, how much extra absorption is there. And time goes from the bottom of this plot to the top. You'll see that there's some masked rows, just low SNR data. The beginning and end of transit are marked by the dashed blue lines. The planetary motion is marked by the pink lines. So remember, this is during a transit. In the stellar rest frame, the planet's moving. So roughly the way to read this plot is there was extra absorption during the planetary transit in the helium-10-830 triplet, roughly correlated with the planetary motion. So we wanted to make this same exact sort of measurement for LTT 9779b and see if its atmosphere was indeed escaping at this very high rate. But the system is located in the southern hemisphere. And until June of this year, there were no spectrographs in the southern hemisphere that could make this measurement. June of this year, I went down to Las Campanas Observatory for the first science run of a new instrument called WINERED on Magellan, which is a high-resolution spectrograph that covers the helium-10-830 line that we're very lucky to have access to here at the CFA. And here's what I found. Do you see the big absorption signature? Neither do I. Right? So across 2 nights of observation, we saw the exact same thing, absolutely nothing. There is no sign of helium-10-830 absorption in this planet's atmosphere, which was an absolute surprise to us. And especially during the first science run, you always want to make sure that you didn't mess something up during the observation, but it seems like this wasn't the instrument's fault. To give you a sense of how well it's performing, here's an example of a detection with Keck NearSpec, basically the best instrument on Earth to do this kind of study before WINERED. This is work by James Kirk, and what I'm showing is the extra transit depth as a function of wavelength. And here overlaid is the same transmission spectrum for our 2 nights of WINERED data. So this is an extremely precise measurement. This is basically having access to Keck NearSpec in the south. So at this precision, if there were a planetary outflow, if there were a strong planetary outflow, we would have certainly seen it. And the fact that we don't, I think, is telling us that planets can survive in the Neptune desert because their outflows are much weaker than we theoretically expect them to be. Now, I'll just close by mentioning 2 reasons why this may be true. First, the star just may not be outputting that much X-ray and ultraviolet radiation, and indeed, folks have looked with Chandra and with XMM Newton and see that the star is a relatively weak XUV emitter, or X-ray emitter, excuse me. Second is a high metallicity atmosphere. The planet has some indication of having a high atmospheric metallicity from other observations. Metals can cool planets, can cool their outflows and reduce the amount of energy available to drive the outflow. And so maybe that's also a contributing factor as well. But this is why I think that there are planets in the Neptune desert. Thank you.
There are 2 other factors that you didn't mention. One is the possibility that the stellar wind is sweeping whatever evaporates. And the second is the tidal effect of the star on the planet. Is that negligible?
It's not negligible. It should actually be making the outflow stronger, actually.
Right. That's right. So one is stronger, but what about the wind?
Yes, so the stellar wind certainly could be a factor confining the outflow, but I'm not sure that we've seen evidence yet of an outflow that has been turned off by a stellar wind. It'll geometrically confine the absorption, but there is still some, unless the wind is very, very strong, which I'm not sure we have any reason to think, it shouldn't completely shut off the helium signal.
And the tidal is important, tidal force, you're saying?
Yes, it is important, and it should increase the mass loss rate above that 10 to the 11 gram per second that we expected. That's a pure photoevaporation rate, but it should actually be higher.
Okay, that's a puzzle. Any questions, comments? Go ahead, Eric.
Why wouldn't you expect a continuum of planets going from the hot Jupiters down through to if it's photoevaporating continuously rather than a gap?
Yeah, that's a great question. So two possible answers. One is a timescales argument. It just happens very, very rapidly at the very start of a planet's lifetime. And it either happens very rapidly at the start and you end up with things in the desert, or it just, they just miss it and they end up living right where they formed. The other option is that these planets formed differently. So perhaps the hot Jupiters got to their current positions by a mechanism like high eccentricity migration, but these planets formed or arrived at their present positions much earlier. And because the star is much more XeV luminous at early times, that will change the amount of mass that the planet loses. So it's not clear which of those cases holds, but both are possible.
Okay, any other comments? Yes, please.
Are there, like the other planets in the triangle, do we know anything about them? And or have you seen something similar, like non-helium detections, non-hydrogen detections?
Yeah, good question. So I think most of them have not been searched yet, actually. Partially because of this whole southern hemisphere situation, partially because they were just discovered in the last year, at least 3 of them were, and partly because a few of them are quite high density, and so that makes seeing these signatures really challenging. But that doesn't mean we shouldn't look. I mean, even if there's a little bit of hydrogen and helium, there might still be a possibility to see this sort of signal. So we should do that.
Is your gut feeling that the theories are wrong?
My gut feeling is the theories are not accounting for the metallicity of the planet. I think that, yeah, in general, envelope metallicity for these planets is probably underestimated as an effect of the mass loss rates.
There was one more question. Go ahead.
Because the claim thing in the radio about?
Yeah, good question. I'm not sure, but I think if this part of the story holds, the high metallicity thing, I think that will have like a lot of impact on the Radius Valley story that we usually tell, where it's like, oh, we have a hydrogen-helium atmosphere, it's just photoevaporating. But even if these things have like 10 to 100 times solar in atmospheric metal content, that apparently can change the mass loss rate by at least an order of magnitude, which is pretty big. So I think it will change the story.
It definitely changes the sound speed, so that.
Yes.
Yeah. Okay, well, let's thank Shreyas again.
Can folks hear me? Good afternoon, everyone. Thank you for having me here today. I want to give a special thank you to Dr. Rudy Montes, who has been my research mentor before I started graduate school. He's been in my corner ever since. And my background is actually in post-AGB binary systems, but today I'll be talking about flares and the current work that I'm doing with my team on the topic of red dwarf stars and their activity across several wavelengths. We want to better understand how this radiation looks like and how they may affect planet atmospheres. So just some background, we know that from Kepler and other ground-based observatories, they have ensured us with statistical certainty that there are more planets than there are stars in the galaxy. And TESS has continued this legacy, hunting for exoplanets, but also opening a new era of stellar activity. And we know that extreme space weather around these stars is a key consideration for exoplanet atmospheres and the search for habitable planets. So really quickly, M-dwarf stars are cool, low-mass stars that range about half the mass of the sun and smaller. They evolve very slowly. Their temperatures are between 2400 Kelvin to 4000 Kelvin. And it's their low temperature that dictates their red appearance. And they're too dim to be seen by the naked eye. Despite their small sizes, though, and faint glow, one of their properties is that they're highly magnetically active. And this is due to rotation and their convective cores. And they have really strong magnetic fields in these stars. And this magnetic activity can actually inhibit convection, creating star spots on the surface of the star, where these magnetic field lines come in and out of the surface. They get tangled up. Eventually, with the process of magnetic reconnection, they snap, and a huge release of stored energy is erupted in the form of flares and energetic particles. And so here we see another picture showing that. And here on the right, we see a picture of a classical flare showing the different regions where we can get the different types of radiation. And this activity can be detrimental to planets orbiting these types of stars. They can produce strong flares with energies up to 10,000 times the strongest flare that has been observed by the sun. And so we want to understand how this can affect these planets. In contrast, M dwarfs may give too little ultraviolet radiation to trigger what is called abiogenesis, which is just the origin of life. And you need ultraviolet light to kickstart that prebiotic chemistry. And so here on the left, we have a flare frequency distribution where we have cumulative number of flares per day versus their energies. And usually flares follow a power law. So in other words, stronger flares are less frequent. And here in this diagram, we show that zone that with the energy needed to have abiogenesis, and then also ozone depletion that can be detrimental as well. And so our group at Goddard, one of our biggest questions is the study of stellar activity. And so here's just some pictures of our group. We have a variety of different expertise looking at different data sets. And this beautiful image was actually created by our colleague Jordan Ely, who's a graduate student at the University of Maryland. And our goal is actually to use simultaneous multi-wavelength observations to provide a complete picture of the evolution of M-dwarf activity using optical data from TESS, X-ray, ultraviolet data from NICER, X-ray data from, SWIFT, UV, X-ray, and NICER observes in X-rays. And so we have a sample of about 30 targets, and with spanning different ages. So I'm just going to touch on a couple of targets today. The first one being YZCMI, which is a very active M-dwarf star. It's about 6 parsecs away with a rotation period of about 2.78 days. And here's a beautiful TESS optical light curve. YZCMI was observed in 2019. And you can see the sinusoidal variation in brightness due to rotation. 2 years later, it was reobserved in 2019, and you can see an intrinsic shift or change in its brightness. And this is due to the evolution of star spots on the surface of the star. You could also see a lot more flares. This is because we obtain data in 20-second cadence, and cadence is important to catch those smaller flares and that we weren't able to see in the 2-minute cadence data. So these strips here, for example, in blue, is the windows of when NICER observed it simultaneously with TESS. The yellow here is SWIFT, and then here in green is VLA radio observations. So zooming into this portion in the 2019 light curve, we can see simultaneous flares happening. And even though we have only 30-minute segments of SWIFT data, we can still catch some flares in all of these instruments. So here's an example of 4 flares, 4 events where we see different formologies. We're currently measuring durations as well as energies in order to construct those flare frequency diagrams. Next, I want to talk about Wolf 359, which is also an active M-dwarf star. with a period of about 2.72 days, a distance at 2.41 parsecs. And it's a very popular star for us because we like it so much. I don't know if you saw this little, anyway. So here's the test light curve for Wolf 359. It's detrended using a package called Wutan. And actually, our colleague Dax Felice, who's at the American Museum of Natural History, is working on the tests and actually K2 data simultaneously, and he provided this light curve for us. And so the strips here are in gray are nicer observation windows. Yellow is Swift, and pink we have XMM Newton data. Here is a broad view of the simultaneous light curve, where we have the tick marks denoting where we find flares. We have from optical all the way to X-ray. And again, here's some more examples of simultaneous flares of two events. Being that I work more on the ultraviolet observations, here's just some preliminary results on the correlations that we expect. So here on the y-axis, we have flare duration versus energy, and then amplitude versus energy. So this is just saying that flares with higher energies occur over longer timescales and also have higher amplitudes. And lower energy flares occur over shorter timescales and have shorter amplitudes. We also have X-ray flares, and our resident X-ray astronomer, Rishi Paudel, is leading the X-ray observations. He's also the lead for our survey paper, and here's just some examples of an X-ray spectrum taken during this event here. So this is an ongoing project. Still, we have so much data, so we're still working on it. But here's more results on those flare frequency distributions, where we're comparing optical, X-ray, and UV. So this is a collaborative working project, and so this is still not done. We have some next steps that we need to do in the case for these particular targets, but in the meantime, we do have a paper out on the target EV-LAC, which is also an M-Dwarf star and is published on AppJ. So this is understanding planet habitability. Also starts with stellar activity. So it's a multidisciplinary scientific endeavor, and we're just getting started. So thank you.
So with respect to habitability, obviously the habitable zone is closer to the M-Dwarf because it's fainter than a sun-like star. So then the planet is more vulnerable because it's closer in. But you can also extrapolate your rate versus energy plot and ask, after how long will there be a catastrophic energy release that will remove the atmosphere from a planet? Do you know the answer? And how long do you need to wait before the energy release will be such that an atmosphere will not survive on an Earth-like planet?
We don't know the answer yet, but I think we can make those estimates. In our ultraviolet flares, for example, we do get those energetic flares in the.
I mean, even if it takes once per million years, that's fast enough not to have life.
Yes.
Every million years you remove the atmosphere.
Mm-hmm.
But you don't know how frequently you have such flares. I mean, if you extrapolate.
They're less frequent, but definitely they do happen. Yes.
Morgan?
Kind of along those same lines, do we know if there is like a cutoff scale? Like, does this power law can't continue forever, right? And so, have we been able to observationally constrain like those rarest, highest energy flares?
I think
do
so.
they have a total energy similar to the convective energy in the star, or something else? I'd be curious where that holds.
Well, in fact, there should be a cutoff in this plot. The total energy that the star can release is limited.
Yeah. Yeah, there are definitely. I would have to go back in the literature, but yes, I think there's an answer to that.
Amazing.
Probably around 35, 36, 10 to 35, you can't release so much energy in one flare.
Yes.
Anyway. But one can estimate it from the convective energy. Any other comments? Okay.
Do your correlations of energy and timescale tell you something about the mass that's kind of thrown out with each of those flares?
Yes.
Not in a
but-
like super direct way, but probably through some modeling.
Yeah, some of my colleagues have extrapolated those numbers.
Interesting.
Yeah, one more question here. Go ahead.
Do you expect all M dwarfs at some point in their lifetimes to be flare stars? Is there like a bias in population, or how does this change with stellar age?
Yeah, so for example, mid-M dwarfs are the most active, and they're in a transitional region where they're they're fully convective, and then they, as time goes on, they don't flare as much. But you do see a few flares in older M dwarf stars. But yeah, usually the mid-M dwarfs are the most active.
Just like humans. Well, let's thank Laura again.
Can you hear me? Great. So, hi, my name is Aldana Grichener. I'm currently finishing my PhD at the Technion, and today I'm going to discuss with you the exciting world of mergers of neutron stars and black holes with cores of giant stars. So essentially, these kind of mergers happen when you have a massive binary system, when we have a red supergiant and can swallow a compact object, meaning a neutron star or a black hole, and then the neutron star or black hole performs this common envelope evolution phase where it spirals inside the envelope of the red supergiant, and if the envelope is not ejected before the compact object reaches the core, then we could have this merger where the core is tightly disrupted around the compact object. This tidal disruption can form an accretion disk that later launches jets, and all kinds of these interesting things can happen in these jets. So essentially, for me, the most interesting thing that I focused on during my master's and PhD was the formation of very heavy elements in the accretion disk that is formed around a neutron star as it merges with the core of a giant star, because we have like these really high densities and temperatures where we have electrons that can join to protons and form neutrons, and we have a neutron-rich accretion disk that could lead to heavy element formation. And the second thing I focused on was the emission of very energetic neutrinos prior to the merger of a black hole with the core of a giant star, because there we could have, like, while the black hole is orbiting inside the envelope, we could have these relativistic jets. And in this relativistic jet, we have protons that interact with photons that forms later very energetic pions that decay to neutrinos in a chain. And these neutrinos could actually be detected by the Ice Cube Neutrino Observatory. But apart from that, these kind of mergers could lead to all sorts of interesting transients that would be classified as peculiar or rare supernovae, as we can see over here. And all these things that you can see here in the motivation was what motivated me to perform a population synthesis study of these systems, because mainly during my master's and my PhD, I used the stellar evolution codes to show the feasibility of the scenarios that I briefly mentioned. But now I wanted to see, okay, so this can happen, but if the event rate is very low, so it would be subdominant and would not contribute much to observations. So for that, I used the population synthesis code called COMPASS. Actually, what we do in population synthesis is that we have a set of parameterized equations to account for the evolution of binaries in this case. Because it doesn't do the entire evolution as in the case of a stellar evolution model. We have like these connections between the different quantities. So in fact, we can have like the simulation of the entire lifetime of a binary system in a very short time, under a second. And then we could actually generate a lot of binaries. And in these massive binaries that I did the population synthesis for, I looked for the event rates of neutron star and black hole core mergers that are the system that interested me. And this way I could compare like my results to observations. Okay, but first, before I actually went to compute the event rates, I was also interested in what would be the properties of the massive binaries that would lead eventually to the merger of a neutron star or a black hole with the core of a giant star. And actually find here this interesting trend, which is a bimodality in the distribution of orbital separation in systems that lead to neutron star core mergers. Because when I was thinking about the systems in my PhD, and believe me, I thought about them a lot. So actually, I was thinking only on this large peak of the less wide binaries, but I didn't really thought that there is another population of massive stars that could lead to these events. So what I did was this fun detour where I explored and went deeper into the evolution, into the code, to see what would be the formation channel of these events. So eventually, the first channel, which is the channel I had in mind when I was thinking about these systems, it begins with two massive main sequence stars. When the heavier star evolves into a red supergiant, there is this stable mass transfer between the red supergiant and the main sequence star. And eventually, due to this mass transfer and stellar winds, we have like the core is stripped from the envelope around it and could explode as a stripped envelope supernovae. And if the system remains bound after the kick from the supernova in the case of a neutron star, so it could eventually even the lighter star would evolve into a red supergiant that in its turn would swallow the neutron star or the black hole, leading to this common envelope evolution phase that I described earlier. So from here, there are two things that can happen. The first thing is that if the neutron star or the black hole manages to get into the core, then I assume there is a merger. But if it doesn't, so because this population synthesis code doesn't account at the moment for tidal evolution, it's something that we actually are working on. So if the neutron star or the black hole remains outside of the core, it won't reach the core. And then after a second supernova in the same manner that Wolf-Rayet star explodes, we can get here either a binary compact object merger that could merge or not merge within a Hubble time. So the case the merger are obviously more interesting because then we can have this gravitational wave signature of the system. And this was actually pretty reassuring because I found the same formation channel with the same rates as done previously in the literature, because it's a little hard to constrain observationally neutron star black hole core mergers because of all of the dust from the envelope. So comparing to something like this would send me them in the right direction. So this explains the first peak in the evolution. For the second peak, actually something interesting happens is that instead of a stable mass transfer in this stage, we have an early phase common envelope evolution, where we have these, the core of the giant star and the main sequence star spiraling one towards the other. And then it happens for relatively wider binaries, as I showed you in the plot, because when this kind of early phase common envelope evolution would happen for less wide binaries, then it will always result with the merger of the core with the main sequence at this stage. So it won't lead to neutron star core mergers. So in this phase, because they get closer together, we get like the same evolution channel as we had before. It keeps going in the same way. But in this case, it only leads to neutron star core mergers, and it will not lead to binary neutron star mergers. And this is actually something I tried to understand while looking at my data and my simulations and even in the literature, and actually don't really know why. So if any one of you have idea or thoughts about that, I really really happy to discuss this afterwards. But anyways, I left this on the side at the moment. And this is actually, okay, so this was the explanation for the second more peculiar peak I actually didn't expect to find. And after I solved this mystery, I said, okay, so now I will go to the things that interest me. The first of them is the formation of variable elements in the accretion disk that is formed around a neutron star as it merges with the core of the giant. So essentially from here, I found the event rates. So here in this graph over here, we have what would be the percent of neutron star and black hole core mergers relative to core collapse supernova for different model parameters that I use. The x-axis is is for the common envelope efficiency parameter that I varied in my simulations. And I found that for like the standard model parameters, which is about alpha common envelope equals 1, which means the entire orbital energy of the neutron star or the black hole goes to unbind the envelope and eject it away. So we have about 1 neutron star core merger per 100 core collapse supernovae in 1 black hole core merger per 1,000 core collapse supernovae. But because not all of the neutron star core mergers could lead to heavy elements formation, we need to have a very evolved core with carbon and oxygen. So it would be dense enough and warm enough for this. So I found also here on the right panel what is the rate of this kind of system that can lead to our process formation. So if this model were to account for all heavy elements formation, that we would say that the typical value of alpha common envelope for these systems would be around 1.25. But because we think that there are, because of the jets that are launched when the neutron star is spinning inside the envelope, actually we have another energy source that contributes to the ejection of the envelope, which results in a larger value of alpha common envelope. So for our estimations, we can account for at least something like around a few 10%, a few 10% of heavy elements nucleosynthesis. So this is one of the things I checked. The other thing I checked was for my scenario of the formation of very energetic neutrinos that are formed when there are relativistic jets that are launched inside the envelope of a red supergiant prior to the merger of the black hole with the core. So I did some calculations using like the data from IceCube and found this kind of systems could account for about 20% of the high energy neutrino flux that is detected by IceCube. So it's not the main source, but it could be like it's not subdominant. So just in time, I will leave you here my take-home messages, and we'll be glad to answer questions.
So, Aldana, do you expect any systems that have sort of like Thorne-Zitkov objects that have a compact object in the middle with some dressed up with an envelope after this process is done, or do you expect the envelope to explode always in the form of some supernova?
So, okay, so for the population synthesis simulation, there is no way to distinguish between a Thorne-Zitkov object and the merger. I expect that in most cases we won't have a Thorne-Zitkov object because you have like a really quick deposition of the kinetic energy of the jets in the envelope, which will cause eventually transient. I think so for most cases I don't expect it is a DOE object.
And then the observers won't be able to tell that it's a special type of supernova. It would look like other core collapse.
Yeah, so I think like for them to tell, so because we have like these jet feedback mechanisms where we have like this negative feedback because there's vast accretion, and then we extract a lot of material and we have less material to accrete, so it would have some bumps in the light curve, such like in the case of the IPTF 14 HLS supernovae. So these kind of signatures could differentiate between them and regular core collapse supernovae, but we need to perform more serious simulation to actually do this modeling of the light curve, which would be a really interesting project to do.
Comments, Ramesh?
So you were trying to constrain this alpha common envelope so as to reproduce the art process rate, right, basically? So you therefore predict a certain rate of mergers of neutron star binaries. How does that rate compare with what we estimate from, let us say, binary pulsars or from LIGO?
So I have this backup slide here where I did this comparison. Let me find it. But I did this comparison of binary neutron star mergers to the LIGO systems, and they actually showed that for quite high values of alpha common envelope, we still can account for the observations here.
And when you say quite high, like what, 2 or 3?
Up to 5 actually.
Up to 5.
Here, which it means that we have here. So here we have like the rates of neutron star mergers, black hole mergers, and neutron star black hole mergers. So it's consistent with some other papers that do it. I don't know. 5 is a really high value of alpha common envelope. I don't know which other energy source could account for this. So what we find for the jet is up to maximum 2. So, but it is consistent with, it still is consistent and like stops affecting. I think after 6 it shows that we underestimate the black hole mergers.
So that's LIGO.
Yes.
What about the radio pulsar binaries? There are rate estimates from that.
I actually haven't looked at this, but I will look at it. It's interesting to compare it to this as well.
So, Ramesh, are you saying that the two are not necessarily consistent, LIGO with the binary pulsars?
I don't know the current situation.
They should be consistent, right?
I mean, yeah, the universe has made it all consistent. Question is whether these models end up consistent or not. I just don't know. Yeah.
It's interesting. I will definitely look at it.
Okay, any other, please?
So you mentioned this puzzle about how in your second formation scenario, it seems like you always end up with a merger instead of a double compact object at the
Yes.
very end, right? Is that because the early initial comet envelope always sort of pushes it into a very close configuration? I know in detail this probably isn't like the
So-
full answer, but is that kind of on the right track?
So I actually looked at this because this was like one of the first things that I thought on, but it doesn't seem that this initial common envelope evolution pushes them closer than the typical initial separations in the first channel. And in the first channel, we do have this neutron star core merger. So I think it's not the direction to go, but it was one of my first like intuitions to check.
Thanks.
Okay. Well, thank you so much for a wonderful talk.
Can you all hear me? Yeah, thanks for coming. I am Vishal. I'm a postdoc at Sierra, and I work on different aspects of gravitational wave astrophysics. So, LIGO, Virgo, and Kagra, they have detected 90 mergers that involve black holes and neutron stars since 2015. And the fourth observing run, it started in May. And in last 5 months, they have already detected, I think, 57 candidates so far. So which kind of means like 10 mergers every single month. So this run will last 18 months. So at the end of probably next 2024, we might have a couple of hundreds of binary black hole or neutron star mergers. But the question that doesn't let me sleep at night is, where are these black holes and neutron stars coming from? We do not know. We have some guesses. So one guess is they might come from binary stars. So you have two binary stars. They were born together, they die, they become black holes, they merge at some point. The other possibility is that they somehow formed in dense stellar clusters. So you have two stars, different regions. They become black holes, they come to the center, they form a binary, and they eventually merge. So the question is, how do we differentiate between the black holes that come from these two different scenarios? And the most popular signature is at least when I was a grad student, was you look at their spins. So if you have black holes that come from binary stars, they should have aligned spins. On the other hand, if you have black holes, binary black holes that originate from clusters, they should have isotropic spins. Today, I am going to disagree. I am going to say that this picture was not as robust as we used to think. So first of all, where is this picture coming from? So the idea is you have two binary stars. They have spins in the same direction. When they die, they will become black holes. They should have spins in the same direction as well. So there are two key assumptions here. So the first assumption is binary stars have spins in the same direction. That might not be true. So there is this banana survey, which stands for binaries are not always neatly aligned. My favorite acronym, by the way, where they look at spin directions. And indeed, not all binary stars, they are always aligned. Now, the second aspect is when they die, they become black holes and neutron stars. Are they aligned? So there are a few pulsar observations where we have spin tilts and one LMXP, and none of them are aligned. Even actually, these two, they are almost in plane. So we can clearly say that even in the field formation scenario, black holes and neutron star binaries, they are not aligned. So if this is not true, what are the other possibilities? So it's possible that they can have completely isotropic spins, even from the isolated formation scenario. So we do not know where black holes and neutron stars get their spins from. It's possible that they might get their spins from some sort of fallback that happens during the core collapse. They might get their spins from internal gravity waves. So you might have some convective layers outside which can trigger internal gravity waves, and these internal gravity waves can somehow spin up the core of the star. So in this case, these are all completely random processes, which means that you would get isotropic distribution in spins. The next possibility is you can have spins parallel to the natal kicks. So usually when you have a core collapse, it's not going to be symmetric, which means you eject mass in one direction, your black hole or neutron stars get kicked in the other direction. Now, we have known since early 2000s that if you look at young pulsars, their natal kicks and their spins, they are usually in the same direction. So this kind of indicates that natal kicks somehow are responsible for spinning up the neutron star or the black hole. So we can assume that the natal spins are completely isotropic. Does that mean the spins are also going to be isotropic? The answer is no. So this is kind of like the histogram of the tilt as we increase the kick magnitude. So as we increase the kick magnitude, what we see is that we slightly tend to disfavor sources which have in-plane spins, because this would mean you have in-plane kicks as well, and in-plane natal kicks tend to disrupt the binary. But as you increase the kick magnitude even more, we start seeing these very interesting features, and that's because you start tilting the binary plane a lot as well. In fact, if you have this ratio larger than a certain value, you flip the plane by at least 90 degrees. So what was earlier in plane is now aligned. So earlier we were disfavoring in plane. Now at very large kicks, you start favoring in plane kicks. Now the final possibility is, what if you can have spins perpendicular to the natal kicks? Now why would I say this? Because, okay, so we are observing, if you look at young pulsars, spins and kicks in the same direction. But this is almost impossible. So till date, no core collapse simulation has ever achieved this. In fact, it's very interesting that they kind of find the opposite. So for example, this paper by Chan, Muller, and Hager, they looked at the angle between spin and kick, and they find that they are at 90 degrees with each other. And other mechanisms have been proposed as well. So for example, you can have off-center explosions, which can, where the natal kick will spin up the neutron star in this case, perpendicular to the kick itself. Or you can have a symmetric fallback of ejecta, which can also give you spins and kicks perpendicular to each other. In this case, we are going to find the opposite, because we will slightly tend to disfavor aligned and anti-aligned cases, because this means kick is in plane, which can disrupt the binary. And again, as we increase the kick magnitudes even more, we start seeing these very, very interesting features. But what does this mean for what LIGO Virgo is going to see? So for example, first of all, let's look at what the popular model is, which is the black hole or neutron star. They get all their spins from their parent stars. In this case, you would mostly have aligned spins with very small tails with small tails of misalignment, because you have kicks as well. If you have isotropic, it's boring, it's flat. If you have spins perpendicular to the kicks, you slightly tend to disfavor aligned and anti-aligned cases. And finally, if you have spins parallel to the kicks, you start slightly disfavor in-plane kicks. So as of now, but how does this compare to what we are seeing with gravitational waves? Now, if we look at the popular model, it says you have isotropic that comes from the dynamical scenario, and you have aligned that comes from the field formation scenario, which means that you should have a peak at spin up actually. So you should have peak at cos tilt equal to 1. On the other hand, if we look at observations, we see a very interesting feature. Instead, what we see is we see a peak at 60 degrees. Now, this is something that you cannot explain using the popular model that we have. On the other hand, if you have let's say spins that are driven by kicks in parallel to the kicks, and if we also have something like, let's say, tides or mass transfer during the one of these stages, we can easily explain the peaks that we are already seeing. The second thing is, so this was gravitational waves. We can also look at the tilt measurements, let's say from young pulsar or LMXPs. I kind of refer to these like early on. So we have two neutron star plus neutron star cases where one of them is a young pulsar, and we have some tilt measurements of this. And we even have one LMXP where we can measure the spin tilt. And what we can do is we can look at the different models. I will not go into the details. We can calculate how much kick magnitude they receive, how much mass loss did they have during the core collapse phase. And we can also do Bayesian model selection between the 4 models that I discussed. And what we find is that the popular model, where all the black hole spin or the neutron star spin is completely coming from its parent, it's kind of disfavored with a base factor larger than 10. So with this, so this is just a recap. The point I'm trying to make is the possibility that black holes or neutron stars get their spins from their parents. That is not the only possibility. We can have isotropic spins, because if in case you have some stochastic processes that spin up your black hole or neutron star, or you can have spins that are driven by the kicks, and these will have their unique imprints on the tilt distribution, which we can see with both gravitational waves and also with in pulsar or LMXPs. And one final key takeaway is, so in general, people used to believe that if you have a system which has large spill tilt or misalignment, or it has, let's say, negative chi effective, or if it has, let's say, if it's highly precessing, it has to come from the cluster formation cluster scenario. I'm saying that clusters do not have a monopoly over systems like this. Even isolated formation scenario can do this as well. We do not know how black holes and neutron stars get their spins from. Thank you.
You said at the beginning that you were losing sleep on the question of the origin. We want you to sleep well, so what would be a different flag of the origin that you can suggest that would tell us which origin is the most popular?
Yeah, okay, so one thing I would say, it's very hard. In fact, I have made things harder, by the way, because earlier people used to think you can just look at spin direction and separate stuff. I'm saying no, it's even harder than this. So one thing I usually look for is, we can look for signatures that the other formation scenario can absolutely not do. And in this case, I look for second generation mergers or repeated mergers which happen in the dense stellar clusters. So if you are in dense stellar cluster, you can have two black holes, they merge. And if, let's say, the gravitational wave kicks are not large, they can be retained. And they can merge repeatedly. Now, these black holes are called second generation, and they're very interesting. They have very unique characteristics. So first of all, they're twice as heavy, which means that they can fill the mass gap. And they also have a spin which is sharply peaked at 0.7. We can use these two features to pinpoint which particular source is second generation, and if they are coming from the dense stellar clusters.
Right.
Does that answer your question?
Yeah, definitely. Of course, it could be a globular cluster, but it could also be a nuclear cluster.
Yes, absolutely. Any dense, any star cluster, yes.
Right. Ramesh.
Yeah, so this, the binary evolution scenario, you talked a lot about the orientation of the spins. What about the magnitude? Can you say?
Okay, because in this case we looked at different mechanisms, and all these mechanisms, they give us different answers. So we did not look at spin magnitudes because it would depend on what exact process we are looking at. So for example, let's say if we have spins perpendicular to the kicks, you can look at, let's say, Finney and Sproit 1998 model. In that case, you can have spin angular momentum equals to offset cross the kick magnitude. You can calculate this, but again, there are, using the same mechanism, there are other, to explain the same perpendicular kicks, there are other different mechanisms which will give you different answers. So that's one reason we are not looking at the spin magnitudes. And the same goes for, let's say, stuff like isotropic spins. In this case, you can have internal gravity waves which can spin up the core. They would give you spins of order 0.2, or you can accrete the convective layers. So there are papers by Antony and Elliott from earlier this year, and they predict spins of order 0.5. So so papers disagree with each other on what spin magnitude we are going to get. So we do not know.
Yes, Evan.
So you've sketched out a really interesting story here. One thing that's puzzling me a little bit about the correlation between spin and kick is that it's not obvious which direction the causality should go. It's not really that hard to spin up a compact stellar core, right? So, and I could imagine that then breaking the symmetry that leads to the direction of the kick. Do you have any sort of thoughts on?
So you're absolutely right, actually. So we do not know which way the causality goes. So in fact, in most population synthesis analysis, they are aware that spins and kicks are in the same direction. But what they usually do is they assume that you have spin in one direction and kick has to be in the same direction. We are saying that we do not know if this is what's happening. What we are saying is it's possible that you have kick in one direction and the black holes or neutron stars are being spun up in this. So we have completely reverted what people have been doing for quite some time now. Because again, we do not know.
Thank you for explaining our ignorance. That's very good. Morgan.
So I'm curious what you say we want to still use spins, and you pointed out that you can reproduce some of these shapes. So what do you think we need in terms of like a number of sources to say like this subpopulation has what seems like a completely isotropic distribution, and this subpopulation has a different shape, and that means something about which of these pathways is probably being taken in reality? Like, do you think we can do that already? Do you think we can make?
No, I did try.
Do we need to do
so
that?
okay, so we need, in my opinion, we need way more sources. Because so for example, in this case, we tried doing like a population model. We tried to model this population along with isotropic, and we cannot say anything with very good confidence. And the problem is that spins, unfortunately, they are not measured very well.
Yeah.
And the reason is, spin direction. And the reason is that these black holes, most of them, they do not have high spins detected by LIGO Virgo. If you cannot measure spin directions if the spin magnitudes themselves are very small. So for now, we cannot do this. But as we get more and more detections, maybe in like next 5 years, we might have a few thousand. Maybe we might be able to answer stuff with more confidence, but not right now.
Yeah, that's the right answer of a theorist. We always need more data. Let's thank Vishal again.